What turns a remotely controlled machine into an autonomous robot is self-control. And where does that self-control come from? Well, sensors collect information that is coordinated and used to tell the actuators what to do next. These sensor-guided movements depend on a controller, the part of the robot that makes sense of the sensory information and then decides how the robot is going to react. Now, it's important to realize that a robot controller or microcontroller gives control to the robot. We're talking here about the opposite of something like a remote controller for our television or a handheld controller for a gaming system. The point is that a robot controller is key to giving a robot autonomy. In the vast majority of modern robots, the controller is a computer, specially designed to take as input sensor data and communications from a human operator. The controller is specially designed to produce output signals for actuators and communications for a human operator. Since the controller runs the computer code, it is programmable. To understand the controller and how it works with the sensors and actuators, let's build a robot. We'll bring our tank over and show you where we're headed. Let me show you the robot we're going to build. It's a one-eyed Tadro, and we'll keep the lights up here for a second, and it is going to flap its tail and swim very slowly and gently across the tank here. Now we're going to dim the lights, and what happens when we dim the lights is it's got a single photoresistor, so it's going to change the turning angle of its tail based on the intensity of the light. So it's kind of swimming straight ahead, and now let's watch what happens when we put a light onto its eye spot. See how it changes its behavior here. Okay, so you can see that it's starting to turn towards that light on that side. So this is a very simple kind of robot. It's got a single sensor and a single actuator. In fact, I contend there's no simpler kind of robot that you can build that has less than one sensor and less than one actuator, and look what it does. It responds to the light, and it's just following the light around. We'll take the light off, and it's no longer coming towards me, it's going straight again. So this is a really neat example of building a robot that has a piece of embodied intelligence here. So this behavior is based on the exact arrangement of the body, the shape of the tail, where the sensor is, and then what the programmer has put into the controller as well. Okay, so it's getting to the end. I'll show you one more time. We'll do light up here onto its photoresistor. See what happens? Look at that. It's turning towards the light. Again, keep it simple, stupid, the KISS principle. When we keep stuff simple, we can actually understand how it works. Now to build a Tadro, we can use my favorite microcontroller, Arduino. We'll use the basic model, the Arduino Uno. You can buy one for about $50, maybe less. Arduino uses free software that's available at arduino.com. Now, both the Arduino hardware and the free software, I'll show you in a moment, are open source systems. This means that you can copy, modify, and share your own software and hardware versions for free and without violating any patents or trade secrets. Because they encourage sharing, open source systems are a terrific way to build communities of roboticists who collaborate. Once you see what's going on here, you'll be able to build a Tadro and get it working. Note that a microcontroller like Arduino is more than just a microprocessor. A microcontroller is really like an entire computer on a single chip here, and it also includes inputs and outputs and read-only memory as well as buffers. As for the body we're going to use, it's going to be something right out of the kitchen. It's just, let me get these screws out of here, it's really just a food storage container. Now, let's get our sensor and actuator working together by way of the Arduino. The sensor we're going to use here for a Tadro is called a light-dependent photoresistor. This is a very simple sensor that changes its resistance to electrical current depending on how much light is falling on it. Now let me show you how this works with a multimeter. I'm going to clip one of the leads of the photoresistor here, and then the other one, and then I'm going to turn this multimeter up so that we can read it, and actually just me turning the photoresistor, you can see getting more light on it, the needle changes here. So the resistance is changing. I'm going to put my hand over it now and look at that drop. Okay, and so we're reading about 5 or 6 times 100, about 600 ohms of resistance we have right now. So that's really cool. You can see how that sensor works. So in addition to the input that we're going to need here from the sensor, we have to think about where we're actually going to connect that sensor to the Arduino. So let me unclip it here. And the Arduino has analog inputs here. We've got ground right here as well as power being supplied. And then we have digital outputs right in here, including some ports that we're going to use for our servo motor in just a second. Okay, so that's what's going to happen for Arduino. All right, one of the things that's great about Arduino is that the hardware and software are open source, as I mentioned. So I'm going to go grab my computer now, bring it over, and we'll put some of that open source software onto it so we can begin to run things. The way we communicate with the Arduino is through a USB cable. So let me open up my computer now. And in the Arduino IDE, the development environment, if you go under File and Examples, you'll find the programs that I'm talking about here, knob and sweep. They will be under the servo samples. And so I think what I'm going to do here is load up the sweep program, which is going to move our servo. Now I haven't shown you the servo motor, but it's sitting right here. And we've got that yellow wire in addition to our power wires, which is always indicative that we've got a servo motor at hand. Okay, so I've called up the sweep program right here, and I've got it connected to Arduino. Now Arduino is getting power through this cable, and you can see that because those LEDs are lit up. So I'm going to click on Upload on the sweep program, and you can see that LED is flickering right here, which tells me that it was just uploading. Okay? Now I have to hook up the servo motor. I'm going to use one of these yellow jumper wires that I created, and I use, by the way, wires for this that are solid core. And you have to distinguish between solid core and what is called stranded wire. And we use the solid core because you can actually plug it in here. So I have to do two things. I'm going to connect the servo to the 5-volt power supply. So I'm going to take the red, which is positive, and that's the middle wire here. And I'm going to hook that up. There's a port here that says 5 volts on Arduino, and I can just put that solid core wire in here. Then I'm going to take a jumper, another solid core jumper, from the black or ground port of the servo, and I'm going to plug it into one of the 2 ground ports. So that's going to provide the power. And I should unplug this before I try to power up the servo. Now it's in there, and now I'm going to use one of these ports for controlling the servo, and it's port number 9, and that's going to provide the pulse width modulated signal to run the servo motor here. Okay, So I've compiled and loaded the knob program, the sweep program, onto Arduino. So let me show you this in operation. It should run again if everything goes right here. We got a little jerk out of the servo. Perfect. So you can see what's happening here. I've painted one of the horns on this servo dark, so you can see it sweeping back and forth here. Very cool. So right away, using Arduino, we're controlling a servo motor. This is great. So we have a connection to Arduino here. The next thing we need to do is now to hook up the sensor, and we need to first of all build what's called, very quickly, a voltage divider. And so a voltage divider takes two different resistors and splits the difference that they cause in the voltage coming through. And so in our case, by putting a variable resistor in the shape of a light-dependent resistor into that circuit, that's going to change the voltage output that the Arduino is going to read. So this is a really slick little circuit. Now I actually have an Arduino that I've already wired up over here, and I've just showed you how this operates. So I'm going to do this. I'm going to make sure I've got my wiring correct by looking over here, and you can keep track. And so I need to hook up here's my fixed resistor right here, and my light-dependent resistor here, and they are going to share a yellow cable here. So I'm just going to do this by not even pulling out the soldering iron, which you could do if you'd like. I'm just going to twist these together, like so, and put a little bit of electrical tape onto those wires to hold them together. Now, if you want your TADRO to have any kind of staying power, you're going to want to use solder. But just to make sure we've got things right, we can just do it like this by twisting the wires together. Okay, so in addition here, what we're going to do is take out of the fixed resistor here, we're going to connect up to our 5-volt power supply. So here what I'm going to do is I'm going to actually unplug that 5-volt power supply from the servo, because I need to hook it up to our fixed resistor. And again, I'm just going to quickly twist these things together, like so. A little bit of tape. And looking at, it's helpful when you color code everything. And then I'm going to take another black wire and connect that black wire to the photoresistor, or light-dependent resistor, like so. Kind of looks crazy, doesn't it? All right. So from this voltage divider that we made, you can see that we have 3 different wires coming. A wire that splits the difference, we talked about it, and a black wire which signifies ground, and a red wire which is going to signify getting that 5 volts that we need. All right. So I can see here that I've got that 5-volt connection, and what I'm doing in this circuit that I'm not actually going to do for us is I'm not going to put a switch in here. That's just something that we don't need to do right now. And so what I can do is take the servo. Okay, so here we need a connection that's going to the servo and a connection that's going into the power supply on the Arduino. So we're just going to twist those together. We're almost there. Hang on for a second. And we're going to combine the sweep program that we know controls our servo motor with another program called knob, and we'll make the combined program available to you. Nick Livingston and I worked on that together. And so that program will actually hack or pull together these 2 examples to run this TADRO for you. Okay, so we have put together our power. So we're going to have our 5-volt power coming out of here. And, okay. And now we want one of our power going into back into the servo, like so. And then we need to have that yellow from our voltage divider go into the analog input A0, which is that analog input channel. So we need that. That's where the Arduino is actually going to read what's going on here. Now we just have, in our circuit, very simple circuit, we just have one loose end here. It's black, and that goes into our final ground position on the Arduino board. And here we go. Now I'm going to call up this combination of the sweep and the knob programs. So this program is Tadro1i, and I've also told the program that I'm working with an Arduino Uno microcontroller. So it's still running the last program that I loaded, which was the sweep program. So now I'm going to tell it to upload. It's stopping, and I'm reading on the screen that it's done uploading, it's compiled it. All right, so we have the Tadro1i program loaded up onto the Arduino. It's good, we see the servo moving back and forth, so that's the code we've borrowed from that sweep program. From the knob program, what we've borrowed is a change in resistance will change the offset of this servo motor. So our resistor that's going to change here is our light-dependent resistor. So I'm going to put my hands on it, and I want you to watch this black horn here. Now do you see how it's going from about 6 o'clock backwards to about 4 o'clock? Watch what happens when I cover up that photoresistor. See, now it's going from about 5 o'clock to 3 o'clock. I'm going to take my finger off. You see how it makes that little jump and goes back down to maybe even 6 or 7 o'clock there and back up to 5 o'clock. Cover it up, and now it's jumped up. It's gone up in time. So that's super. That shows me that we've got a circuit here that's taking sensor input and changing actuator output. Very cool here with the Arduino. Now, our trick is going to be to put the Arduino in here. And what are we going to do for power? Well, I'm going to do something that's really easy. I'm going to use a USB power supply. You can get these all over the place. And you could also use batteries, but that involves hooking up, doing a little more wiring, which we're just going to avoid here. So I've got this USB power supply here that I'm just going to put in our little boat, I'm going to start calling it, our boat upon the sea. And it's okay for the moment if it's popping up. And I don't want to plug it in yet because that's going to turn on the Arduino. And now we have the issue of how do we mount this servo motor. And so here's my hot glue gun. Now, when you use hot glue, you have to be very careful not to get the glue on your finger when you're first putting it on, because you will burn yourself. So do take care here. Now what I'm going to do is just actually literally hot glue this servo motor. You know, there are slick ways to do it, and I'll show you how I've done it on the other Tadro that I've got here. But we're just trying to get this thing working initially and in place. So I'm going to hot glue it there, hold it for a second while the hot glue cools. All right, and I can already feel it setting up. That's the great thing about hot glue. It sets up very quickly. It's not particularly strong, but you can set it up very quickly. And if you make a mistake, you peel the hot glue off. And the next thing we're going to do after this is we're going to make a tail using this little wooden dowel that I've cut. We're just going to wrap duct tape around that wooden dowel and attach it to our servo. So there we go. I've just hot glued that servo into place, and we're almost there. Next up, I have cut a piece of duct tape, and that duct tape is going to act as our propeller here. And now the next thing I need to do is just glue that tail to our servo motor. So I'm going to put hot glue here. Oh, I should stand up the hot glue gun and get it out of my way. Right here. And here we go. I'm just going to press it. Like so. You can see that's kind of loose with the servo motor, so it's not a great connection. So I could go in and do some more hot glue in a second. Okay. So we have our hot glue on our tail, holding it in place. And we have one final thing to think about, and that is where the sensor is. So the sensor's up here, and I'm happy with that. It's pointing forward. So now I'm going to go ahead and plug this in. And again, it doesn't look as slick as our other one. We'll take a look at that in just a second. And I heard the servo go. And we would tuck that cord inside. And in just a second, our tail's going to wag. Check it out. Our tail's wagging. I'm going to hold my finger over. There was that big jump in the tail. Okay, here comes the light. It's going to switch in just a second. Okay, it's made a little turn there, and that would turn it in the water when it was swimming. We've just made a Tadro. Now, I told you we can do this a little more slickly with some time here. And this other Tadro, what I've done here is cut out of the lid, kind of a splash guard. I've put a switch in here, and I've also used a battery. And then on this side, you can see I've made a little mount for the servo. I've actually made a plastic mount down here, used some more hot glue. But once you have the basic Tadro going, you can make it as pretty as you like. When we think about the purposeful movement of the whole Tadro, we can now put the sensory actuator circuit into its place in the functional loop of an autonomous robot. The movement of the Tadro changes the amount of light that falls on the sensor, and the whole functional loop starts all over. Sensor reading changes actuator movement. Actuator movement changes sensor reading. Since the conversion processes that take place on board the robot give the robot self-control, it makes sense to call this part of the system the controller. One of the very first robots that had a digital computer for a controller was Shaky. Shaky was a mobile robot built by researchers led by Charles Rosen at the Stanford Research Institute from 1966 to 1972. And at the time, digital computers were large and heavy, the size of a bank of industrial refrigerators, filling a good-sized room. Now, the final version of Shaky used a Digital Equipment Corporation PDP-10. The PDP-10, by the way, loomed large in hacker lore because it helped the Internet take baby steps as part of the Internet's precursor, the ARPANET. And it was very advanced for the time and used at only a few universities. But the PDP-10 could never, ever fit into a robot the way an Arduino can now. So to serve as the controller of Shaky, it had to be in constant radio communication in order to be Shaky's sensory actuator loop. While Shaky was revolutionary in putting artificial intelligence into a sensor actuator circuit, the idea of using radio waves to communicate with a mobile vehicle was not revolutionary. The concept of remote control was actually patented in 1898 by that genius of electricity, Nikola Tesla. In his patent, Tesla describes what he called teleautomation, what today we call radio-controlled or remote-controlled vehicle. And he demonstrated his idea at the Madison Square Garden with a 4-foot boat, which he controlled using a telegraph signal box. Now, Tesla did not discover radio waves or invent the devices to produce them, but what Tesla did do was build actuators that could be controlled remotely. Propulsion and steering were his targets, and he demonstrated a remotely controlled boat to the public. What we see in many different kinds of robots, by contrast, is neither Shaky nor the Tesla robot, but something we call partial autonomy or partial remote control. The robot has some autonomy, and a human operating remotely shares control with the robot. Now, when we think about full self-control, full autonomy, what I'm psyched about is this. We can treat sensor motor circuits as discrete building blocks where each block is a behavior module. And those modules can function independently, and those modules can function together with their coordination decided upon by the controller. This focus on behavior modules was developed and made famous by Rodney Brooks when he was a professor at MIT, and this approach goes by the name of behavior-based robotics. The hallmark of behavior-based robotics is that the controller makes decisions about which behavior module gets to operate when. Now, because this is an all or none proposition, we think about this as the behavior modules competing to have the controller decide to let it operate. A winner-take-all scenario. No sharing of the actuators. You either are the behavior that is operating or you are not. Rodney Brooks very quickly realized that the great value of behavior-based robotics is that you can use very simple programming, like what I've shown you on the Arduino, to get robust self-control out of your robot, autonomy. With this in mind, let's take a quick look at one of Brooks's creations, Roomba. So, one of the great things about Roomba is it has many sensors on it. It's got a bump sensor, it's got cliff detection sensors, and it's also got the ability to find its way back to the charger. I'm just going to turn Roomba on here, and we're going to do a quick experiment to see how the different behavior modules are both connected to the sensors and organized. So right away, I'm going to touch the bump sensor, and you can see it goes into escape. Okay? Now I'm going to hit dock, and what the docking should do is override everything else. Okay, let's hit dock, and then Roomba's going to find its way back to the charging station. There we go, Roomba. So what we saw is that the escape behavior overrode everything else, including cleaning, that was more important, and when I hit dock, it changed its behavior as well. Now we've learned something about Roomba's controller without having to look at its code. We could do similar pairwise comparisons like rock, paper, and scissors to see which behavior is programmed to win in which situation. We're always comparing our current perception of the state of things with our desired goals and things like, are we there yet? If not, we keep going. If yes, then we stop. So this comparison of have we achieved our desired goal to where we actually are is at the heart of self-control, and the general principle is what's called negative feedback control. Negative feedback is one of the most important principles that governs the control and regulation of mechanical or even organic systems. In fact, the fields of cybernetics and engineering control theory are built around issues of feedback control. We can see negative feedback control in action using Baxter. Now, I've taught Baxter to pick up a cup, place it right over on the other side, release it, and then pick up another and do the same. Now, I'm going to be mean here and move this other cup from where it was. Now, this would completely discombobulate a traditional factory robot that is moving from place to place, but not Baxter. What does Baxter do? You can see Baxter, first of all, recognizes that the cup was not there. It's not trying to blindly pick up the cup. It's trying to find the cup. And here's where the negative feedback comes in. It's trying to minimize the position, I'm going to trick it again here, between its desired position and the actual position of the cup. Here we go again. I'm going to put the cup in place. You can see how it made an adjustment, and now it's found it. It's going to move the fingers in here, and you can see how it wiggles back and forth a little, just like you do when you're steering a car, trying to figure out exactly where that was. It's in a search pattern here to look for more cups. They aren't available, so there's nothing for it to do in terms of negative feedback. But that's how it works in Baxter. Putting a robot in the driver's seat is the fundamental issue in robotics, and the controller is how we do it. A controller is a special kind of computer whose program modules give autonomy to a robot. The biggest questions in robotics often revolve around what combination of autonomous self-control and remote control by humans are most appropriate for a given situation or robot. But robust autonomy, that is, working with self-control in complex circumstances, often requires two kinds of autonomous control. A hybrid type of control architecture. We've got behavior-based processes, which are quick, sense, and react. And then we have model-based processes, which offer long-term goals, sense and plan, and then move. How much autonomy to give a robot is the biggest question, but the answer often involves a second question. What kinds of autonomy will the robot have? Both in the design and the operation of a robot, the controller is how any robot's autonomy is created and defined in the linking up of sensors and actuators. The controller is where a robot's autonomy is overruled by humans or extended even further.